In the previous module, we have learnt about the emission of radiation from a black body on the basis of particle nature. Now let us look at the photoelectric effect, which is also explained on the basis of particle nature. In 1887, Hertz performed an experiment in which he observed that when the surface of certain metals, such as cesium, potassium, sodium, rubidium, and so on, are exposed to a beam of light as shown, electrons were ejected. This is called the photoelectric effect. The electrons thus emitted are called photoelectrons. From this experiment, the following observations were made. 1. No electrons are ejected from a metal if the incident light has frequency of less than a certain minimum frequency value, called the threshold frequency. 2. The number of photoelectrons ejected is directly proportional to the intensity or brightness of the incident light. 3. The kinetic energy of the ejected electron is directly proportional to the frequency of the incident light. These observations could not be explained using the laws of classical physics, according to which the number of electrons ejected and kinetic energy associated with these electrons depend on the intensity of the light radiation. However, it is observed that the kinetic energy of the ejected electron depends upon the frequency of the incident light, but not on the intensity of the light radiation. For example, when the metal potassium is irradiated with high, intense red light having frequency of 4.3 to 4.6 multiplied by 10 raised to the power of 14 Hz for hours together, no electron is ejected. But as soon as it is irradiated with even less intense yellow light having frequency of 5.1 to 5.2 multiplied by 10 raised to the power of 14 Hz, photoelectrons are ejected. This is because the threshold frequency for potassium metal is 5.0 multiplied by 10 raised to the power of 14 Hz. Einstein explained these observations of the photoelectric effect, for which he received the Nobel Prize in 1921. He has taken into account the Planck's quantum theory of electromagnetic radiation for explaining the photoelectric effect. Note that the quanta were called photons by Einstein. According to Einstein, electrons in metals are held by attractive forces by the metal kernels, that is, the positive ions of the metal. To overcome these forces, the photons of incident light must possess a certain minimum energy, so as to release an electron from the metal surface. Thus, when a photon of sufficient energy strikes an electron in the atom of the metal, it transfers its energy instantaneously to the electron, and the electron is ejected without any time lag. From the quantum theory of radiation, we know that the energy of the incident photon is directly proportional to the frequency of the incident light. The minimum frequency that provides enough energy just to release an electron from the surface of a metal is called the threshold frequency, designated as nu0. Hence, when a beam of light, that is, a beam of photons, strikes the surface of the metal, electrons will be ejected only if the incident photons have the frequency nu greater than the threshold frequency nu0. Let us assume that the frequency of the photon of incident light nu is greater than the threshold frequency nu0. In other words, the striking photon has energy equal to h nu, and the minimum energy required to eject the electron is h nu 0. As the energy of the incident photon h nu is greater than h nu 0, The remaining energy, that is h nu minus h nu naught, is imparted as kinetic energy to the electron. Thus, h nu minus h nu naught is equal to half mv square. Here, m is the mass of an electron and v is the velocity of the ejected electron. On rearranging the equation, we get h nu is equal to h nu naught plus half mv square. H nu naught is constant for a particular metal and is designated as W naught, which is called work function. Now, the equation in terms of work function is as shown. Let us observe the values of work function for a few metals. Hence, if the energy possessed by the photon is high, the energy transferred to the electron is also high, and hence the kinetic energy of the ejected electrons is also high. In other words, greater is the frequency of the incident light, greater is the kinetic energy of the ejected electron as shown in this graph. Lastly, greater is the intensity of incident light or the number of photons that strike a metal, greater is the number of electrons ejected. For example, when more and less intense yellow light is made to shine on potassium metal separately, then relatively more number of electrons will be ejected from the potassium metal irradiated with high intense yellow light.